Hello everyone, welcome to our presentation. My name is Kucheki and I'm a researcher in the Welding and Joining Research Center at IUST. Today I'm going to talk about our study. The title, Implant Fracture Analysis of Biomaterial Adhesively Bonded Joints by using a simple and beam specimen. In this study, I have worked with my supervisors Dr. Aliha and Dr. Razavi. This is the outlines and the one I am going to discuss in this presentation. Applications related to adhesive bonding are today very diverse and can be found in virtually all types of industries such as aeronautical, automotive, steel construction, shoes, electronics, biology, and medicine. Adhesively bonded joints have a number of advantages over mechanical fasteners, including can provide a more uniform stress distribution along the bonded area, can provide good damping properties, can bond dissimilar materials with different coefficient of thermal expansion, can efficiently bond thin plates, and etc. Due to variables such as insufficient surface cleaning, presence of wolves in the adhesive and others, cracks can form at the bonding region on rough-like nose. Various types of loading cause three types of fracture modes at cracked adhesive parts: its opening, in-plane shearing, tearing, and mixity of these modes. DCB, ENF, and MMB are some examples of well-known specimens that can be utilized to evaluate the fracture parameters of cracked adhesively parts subjected to mode 1, 2, and mixed mode 1 and 2 loadings respectively. These testing techniques face a number of challenges and drawbacks, including inability to introduce the full range of mode mixities, need for complex testing hidden fixtures to carry out the test, high cost of testing, and etc. Therefore, designing and proposing new and suitable testing methods for the investigation mixed mode 1 and 2 fracture behavior of adhesively bonded joints is still a necessary and interesting subject. Hence, in this research, a simple and new test method and geometry are proposed for analyzing the behavior of adhesively bonded joints. This new specimen is called Biomaterial Inclined Match Symmetric Short Bend Beam, abbreviated as B-ASBB. Simple geometry is of testing with a conventional three-fold bend fixture, reducing full range of mode mixity from pure mode 1 to pure mode 2. The small size of materials, low cost of testing, are some of the benefits of the suggested B-ASBB specimen. The state of mode 1 and mode 2 mixities can be changed in this specimen by moving one of the bottom spans. Figure 6 shows the overall schematics of the B-ASBB specimen. The overall dimensions of this specimen can be seen according to Table 1. Table 2 and 3 illustrate the mechanical properties of the selected materials. The left and right materials creating the B-ASBB specimen can be either similar or dissimilar. Here, aluminum ceramic and aluminum metal alloy, abbreviated as AL, were considered for joining by an epoxy adhesive to manufacture the B-ASBB specimen. In Figure 7, the finite element model of the B-ASBB specimen based on the J-contour integral method created in the American commercial code is visible. 7600 CP8S8 note by quadratic plane string quadrilateral elements were followed in total. In this study, it's assumed that a crack in the adhesive part and this part is considered to behave as an inelastic material. The stress and geometry factor of the B-ASBB specimen are according to equations 1 and 2 respectively. Stress, which is defined via dividing the bending moments and of diagonal geometry to its section modulus A. Figure 9 shows the variations of mode 1 and mode 2 geometry factors as y1 and y2 obtained for different S' over n ratios. It can be seen that by decreasing S prime over a ratio from 0.7 to about 0.04, the contribution of mode 1 decreased and conversely mode 2 component increased. Indeed, the SIF ratio, that's K1 over K2, approaches to zero, showing switching the state of corrective deformation from pure opening mode for S prime of R equals 0.7, in which Y2 equals 0, towards pure shear mode, that's Y1 equals 0 at lower loadings and ratios. And also, according to figure 9, the alternate material types located in the left and right hand side of the B-ASBB specimen subjected to mixed mode 1 and 2 loading change slightly the fracture parameters. It is finally noted that using several finite geometry analyses, we demonstrate the ability of the B-ASBB test specimen for producing any desired mode 1 and 2 mixed. This ability, in addition to other advantages of B-ASBB specimen, including simple geometry, sub-size dimensions, and ease of testing, makes the B-ASBB specimen as a favorite testing specimen for analyzing the mixed mode 1 and 2 fracture behavior of adhesively bonded joints. Thanks for your attention.